Hello, welcome back to the session. Previously we have seen what is the definition, application and the ROC of ZT. Now we'll try to look into some of the problems for Z transforms, some of the standard problems. So here I have taken a problem which is very basic problem, and the problem is given as find the Z transform of x of n equal to u of n. Here we need to understand that u of n is a right-handed side sequence. I have also shown the diagram while calculating it. So we know that x of z is given as n equal to minus infinity to infinity x of n z to the power of minus n, as we have seen in the last session. X of n is given as u of n. This is the question that is given, and we know that u of n is defined as, because it is a unit step signal in discrete, so u of n is defined as 1 for n greater than or equal to 0, and it is equal to 0 otherwise. This is a mathematical representation. If I try to convert it into a graphical representation, then according to the definition, n equal to 0 or greater than 0. So from n equal to 0 to n greater than equal to 0 means up to infinity, because there is no limit. Greater than 0 means up to infinity. All the values from n equal to 0 to infinity is 1, 1, 1, 1, 1 and so on. And it is equal to 0 otherwise. Otherwise means for n less than 0. For n less than 0 I don't have anything, so I have shown it as 0. So this is the graphical representation, and we understand that there is only the value which is available from 0 to infinity, and that is equal to 1. So the formula becomes x of z equal to n equal to minus infinity to infinity. Instead of x of n, u of n is given. So I have substituted u of n instead of x of n, and z to the power of minus n is as it is. But I know that from minus infinity to plus infinity I have the value only available from 0 to infinity. So for n equal to minus infinity to minus 1 I don't have any value. For n equal to 0 to infinity I have a value of u of n which is nothing but 1 here. So x of z now turns out to be n equal to 0 to infinity 1 z to the power of minus n. So I am representing it as equation number 1. If you see the formula of summation, this is a standard formula obtained from the geometric progression, where it is written as n equal to 0 to infinity alpha raised to n is given as 1 divided by 1 minus alpha. But there is a condition that alpha should be less than 1, because if alpha is less than 1, then and then only this summation converges. Otherwise this becomes a divergent kind of summation, because if I add n equal to 0 to infinity, even if 1 is added for n equal to 0 to infinity, 1 plus 1 plus 1 plus 1 and so on up to infinity, the answer becomes infinite. Or if the value of alpha is greater than 1, for example 2, 3, 4 and so on, so if you even add 2 infinite times it becomes infinity, or if you add 4 infinite times it becomes infinity. So the condition is very clear, alpha should be less than 1. It cannot be greater than 1. Actually the value of alpha should be somewhere from 0 to 1. If it is 0 to 1, then and then only this is summable. Okay, so if I try to correlate this formula with my summation, so what we have done is that I have replaced this 1. There is no reason to put 1 here, because 1 into z to the power of minus n is z to the power of minus n itself, and this z to the power of minus I have written it as z to the power of minus 1 raised to n, which I have shown here. Z to the power of minus n is written as z to the power of minus 1 raised to n, and summation is from n equal to 0 to infinity, because u of n is given and u of n exists only from 0 to infinity. So if I try to compare this with this, then n equal to 0 to infinity, n equal to 0 to infinity, this is alpha raised to n, this is z raised to minus 1 raised to n. So clearly says that z inverse is compared with alpha. Yeah, z raised to minus 1 is compared with alpha. So alpha is nothing but here z raised to minus 1. So if I put it in this formula, this is 1 divided by 1 minus alpha. Alpha is z raised to minus 1. So x of z becomes, so this equation becomes directly 1 divided by 1 minus z raised to minus 1. Condition is alpha should be less than 1. Alpha is z raised to minus 1. So z raised to minus 1 should be less than 1. If I try to solve this part, this will give me ROC. Z raised to minus 1 is less than 1 means 1 divided by z is less than 1. If I take z on the RHS, z towards RHS. So Z multiplied by 1 becomes Z itself. So if I take Z here, so Z must be greater than 1. This one is here. Or the same thing I can write it as like this. Z is greater than 1. Magnitude of Z must be greater than 1. If I try to solve this part, 1 divided by 1 minus Z inverse. Z inverse can be written as 1 by Z. And if I take LCM, Z becomes LCM. So Z has to be multiplied here. So Z minus 1 divided by Z, because Z is multiplied here. So Z into 1 is Z minus 1 whole divided by the LCM, that is Z. I'll take this to the numerator. If I take this to the numerator, this becomes Z divided by Z minus 1. So X of Z now is Z divided by Z minus 1 with ROC as Z greater than 1. Now we'll try to plot this, and we need to understand this is numerator and this is denominator, which will be helpful for us to calculate the zeros and the poles. We know that whenever we equate numerator to 0, we get zeros, and whenever we equate denominator to 0, we get poles. Equating denominator to 0 is as good as making this X of Z equal to infinity, because anything divided by 0 is infinity. If you are making this denominator equal to 0, then this becomes infinity. So indirectly poles represent that X of Z is infinity there. So we'll try to now plot this, whatever we have got here, into graphical representation. So there it was Z divided by Z minus 1, and ROC was like greater than 1. Z is greater than 1. So what I have done is that I have taken a value of Z which is equal to 1 here in a real part, in a real number. So this becomes the radius of the circle, and then this, the magnitude of Z is greater than 1 means this is the magnitude of Z equal to 1. This is the magnitude of Z equal to 1, and greater than 1 is something outside this circle. So outside this circle the ROC exists, which is shown by a shaded part. So ROC is outside the circle because Z is greater than 1. Magnitude of Z is greater than 1. And for Z less than 0, we don't have any ROC. So the 0 is at Z equal to 0 because numerator is Z only. So if I equate it equal to 0, so that becomes Z equal to 0 only. So Z equal to 0 means 0 at 0. Z equal to 0. And if I equate denominator equal to 0, then it is Z minus 1 equal to 0 because denominator is Z minus 1. So if I equate Z minus 1 equal to 0, this implies Z equal to 1. If I take 1 on the right hand side, this becomes Z equal to 1. So I am having a pole at Z equal to 1. So here it is shown as a pole at Z equal to 1. So pole is represented by a cross, and 0 is represented by a dot or a circle. So here it is a circle at Z equal to 0 and it is a cross at Z equal to 1. So we can see that the ROC is outside the circle. It is not on the circle. It is exactly outside the circle, and pole exists on the circle. So pole is not existing in the ROC. Try to see here, pole is on the circle. Circle is not a part of ROC because ROC is Z greater than 1. So beyond, immediately after 1, the ROC starts, but not exactly at 1. So we here clearly understand that this pole never falls in ROC. Pole is away from ROC by a very marginal space. So I can say that pole does not exist in ROC. Thank you.